So hello guys, welcome back to my channel Code Shiva, where I post my DSA solutions each and every day, and today is day 15th of doing so. The problem that we will be looking today is ugly number. This lead code problem number 263. So let's see what the problem really is. An ugly number is a positive integer which does not have a prime factor other than 2, 3 and 5. Given an integer n, return true if n is an ugly number. So what is here? We are asked to find if a number is ugly number or not. If a particular if a particular if a particular number is ugly number or not an ugly number. Okay, so this is what we need to, not an ugly number, this is what we need to find essentially. How we'll be able to do so? We need to look at, first of all, like what an ugly number is. So an ugly number is a kind of is a positive number. First of all, it is a positive number, and second thing, it is a number which doesn't have any other prime factor other than 2, 3 and 5. So if this number would have any of the prime factors, then it will either be 2, 3 or 5, right? For example, there is a number like 12. If we like prime factorize 12 to 6 or 12 to 3, 3, 1. Okay, so if we take all of the factors, if you like take all of the prime factors, 2, 2, 3, like we can just write it one time. So 2 and 3 are prime factors of 12. So 12 is an ugly number. It is a positive number and it has just two factors, 2 and 3. Okay, so this is fine. Let us look at any other example, such as let's say uh, 25. Okay, so 5 times 5, 5 times 1. The only prime factor at like in this number is 5. Since it is one of these three numbers, it can be considered as an ugly number. Okay, it is positive and it has all of the prime factors are none other than 2, 3 or 5. So this is an ugly number. So that's it. These are what we can call as an ugly number. And if there is any number which is let's say if there is any other number which is 20, if we want to like 2, 10, 2, 5, 5, 1, this is also an ugly number. Let's say 36, 3, this is also an ugly number. Let's say let's say 34. Now 2 times 17 and 17 times 1. Okay, so prime factors here are 2 and 17. This is a positive number which takes our first statement as true, but the second statement, which is in an ugly number, all the prime factors has to be 2, 3 or 5. Okay, so we have 2, we've got 2 over here, but the second number that we have got is 17, and this number is other than 2, 3 and 5. So this number cannot be considered, so this number is not an ugly number. This cannot be considered as an ugly number. This is not an ugly number, right? So this is all what we need to do. Now there are different ways through which we can solve this problem. The first one being, let's see, approach. Okay, so now we need to look at different approaches through which we can solve this problem. The very first approach to this problem is prime factorization. Prime factorization, it's simply whatever we have been doing till now. What we are doing is, for a number we are just we are prime factorizing it, and we are looking if the prime factor is one of those three numbers, 2, 3 or 5 or not. if the number that we have got is other than 5, 2, 3 or 5, in the earlier case that we have seen for 34, which was 2 7. Okay, that if there is any number which is other than 2, 3 and or 5, if there is any other number which is a factor of this number, and it is a prime number, of course, this then that particular number will not be considered as an ugly number. Okay, so for this what we will be doing is, first of all, if I can just write a pseudocode for this approach, I would say that at first we can definitely take something as limit. Okay, and limit is what? Sqrt, square root of a particular num, right? Square root of a particular number. We can have a for loop over here, and I, which starts from 2, and it will go till sqrt of num, or at this case we have taken this particular number as limit, right? The reason I'm doing this is because I don't want to calculate every time like square root of a particular number, because it will also have some time complexity. And if we are running a for loop and we are calling this function again and again, then the time complexity of this function will increase. So instead of that, I will be just creating a variable which will store this value of square root of a particular number. So to explain you like this, we are essentially doing over here is we are checking for all of the factors, and we are checking if there is a particular prime factor in a number. Let's say we have a number as 16, right? What we are doing is we will be like, let's take all of the factors of 16. 1, okay, 1 2 4, and then 8, and then 16 itself. Now I just want to tell you how we can like not go, if we want to calculate all of the factors of 16, how we cannot just run like a for loop from which is maybe starting from 1, or like which may be starting from 2 and it is going till 16. We will not be using a for loop like that. What we are instead doing is we will be using a little math over here. How so? So if I'll be just like telling you a proof of this. If we have a certain number, let's say 16, or let's say it is a variable c, and here somewhere lies a root of c. Okay, uh, here will be some factors of c, and definitely like both sides of this root c, we will be having some factors, right? Now what my point is that we will be having a for loop which will run from maybe 2 till root c, and if we calculate all of the factors between this point, we can definitely calculate all of the factors in this block too. And how so we will be doing that? The thing is like, for all the factors of 16, we will be running a for loop from 2 to root 16, which is 4. Since we have factors like 1 2 and 4 at this point, we can get every other factor of 16 by multiplying these three numbers which were smaller than root c or root 16. Like 1 multiplied by 16 equals 16, and 2 multiplied by 8 equals 16, and 4 times 4 equals to 16. So we can just multiply, we can just get every other factor by just iterating till root c. So this is what the logic is, and that is why we will be running a for loop only till root c. Okay, after that what we will be doing is we will be checking uh, if a particular I is exactly equals to 2, or it is exactly equals to 3, or it is exactly equals to 5. What we will be doing is we will be dividing this number again and again by all of these numbers. What we This is exactly what we were doing in prime factorization. Like if we have 2 over here, we are dividing this 12 by 2, and we will be getting another number which is smaller than 2. So like 2, we are getting 6 over here. The number is now trimmed down to 6. Now we will just be doing this, and at last we will get nums as 1. Okay, so if the condition is like if the condition is like this, what we'll be doing is we will be updating n divide equals to I again and again and again. If this is not the case, let's say if there is a number I which is dividing this particular number, and it is not it is a prime number, uh, which is not like 2, 3 or 5, we can definitely return uh, false, that it's not an ugly number, right? We'll just be doing that. Else we can just return false. And at the very last case, what we can definitely do is we can just like after these parentheses, we can check if particular number that particular number at last we can just say that this particular number is an ugly number or not. This is an ugly number. Okay, we can simply have a check over here, which will see if this particular value of n, if n is exactly equals to, or no, we don't really need this check function. So this is everything that we will be doing in this approach of this problem. That's fine. Now the second approach that we will be trying is the second approach that we can try is by continuously dividing a particular number by all of these 2, 3 and 5. We can update n every time. Like we can definitely take a vector in which we will have 2, 3 and 5, and we can like divide a particular number again and again by 2, again and again by 3, and again and again by 5. If a particular number is at last exactly equals to 1, that means this particular number doesn't have any other prime factors other than 2, 3 or 5. But if this particular number is not equal to 1, that means there is a certainly other number which is dividing this number, and which definitely means that this particular number is not an ugly number. Okay, so this is it. Now let's see the implementation part. The thing is that the last approach is clearly very easy to implement, so I will not be like writing a dry run of this, like the pseudo code for this problem, and that's simply it. Yes, so I forgot to mention the time and space complexity of this problem. uh, the first approach of this problem, which is solved by prime factorization, has a time complexity of, like we can have time complexity of big O of root n, and space complexity of like constant space complexity, right? And secondly, for this last approach, we can have our time complexity as since for a particular number which is 2 raised to power 30, like 37 or anything like that, or for a particular number which is 5 raised to power 30, we can have, like we can have our code, we can have our loop running for, like the time complexity at this case would be log 2 base 37, and for this case it will be log 5 base 30. Okay, so the overall time complexity, since this will have the most iterations, we can have a time complexity as in the worst case it will definitely be log of 2n. So that is it. And space complexity, of course we are using a vector over here which has a constant space complexity of 3, and since we have a constant space complexity we can neglect it. Okay, so let's now see the implementation of this problem. Okay, so for a particular number, to be an ugly number, it should be positive. If a particular number is an ugly number, it should be positive. So if a particular number is smaller than equal to 1, smaller than equal to 0, you can just return false. And if a particular number n is exactly equals to 1, we can directly return true over here. Now we can have a for loop, and num, we can create a vector in which we have 3 elements, 2, 3, 5. Okay, and what we can do is while num mod and mod num is exactly equals to 0. If this particular number is dividing this number, then we can update n as and divide equals to num. Okay, we can do this, and then at last we can return uh, n is exactly equals to 1. So if this condition is true, then we will have our answer as true, and if this condition is false, then we will have our answer as false. Okay, so all of the test cases are running. Let's see if our solution works for larger test cases too. Yep, this solution works. So this is it, guys. Thank you for watching my video, and thank you for supporting me, and log out.